I hope these recordings are going well. We'll see. Okay, so this is the third hour of Physics 1C for February 18th, and we're going to look at this problem right here, which says we want to find the resultant force. This is another superposition problem. Make it a little bigger, because I think these are kind of hard to see. It's probably better. So we have 3-point charges that are located at the corners of a triangle, as shown, where we have values for each of them. Q1 and Q3 are both 5, so these two are actually the same charge, just at different locations. And then Q2 is -2, and we know the value of A is 0.1 meters. We want to find the resultant force exerted on Q3. So in this situation, we're basically saying Q2 is fixed in place, Q1 is fixed in place. We are only going to look at the forces acting on Q3 right here. Okay? So, yeah, let's do that. So, in order to do this, we need to first, I think personally, you can do however you want to. The first thing you really want to do is you want to draw the direction of your forces on your picture. So we'll use these vector symbols here to do that. So first of all, we'll look at the force of Q1 on Q3. Now, Q1 and Q3 are both 5 microcoulombs. They're separated by a distance of √2 over A, okay? And the direction of the force is going to have to point that way, right? And we'll use that as our kind of reference vector. And we're going to call that force the force. Instead of doing 1 on 3 and 2 on 3, why don't we just call this F1? Okay. In addition to that force F1, there is also a force that Q2 places on Q3. Q3 is going to be attracted to Q2, so the direction of that force is going to be to the left. Now, in terms of sizes, we won't really know until we calculate it, but we can roughly say Q3 is closer to Q2. It's A versus √2A. But Q2 is smaller than this one. So I don't know what the answer is actually going to be, but these two vectors might be about the same size. I know that F1, if they were the same values, it would be half as big, because it's √2A away. And Q2 is 2/5. They really are going to be really close. I think this one's going to be smaller than this. We'll make it a little bit smaller. I don't even know if that is smaller, because I'm just eyeballing it, but we'll call that one F2. Okay? And I'll move it over a little bit because that A there is... Let me select F... It doesn't really like when you try to... 2. Here we go. Okay, so we've got F1 and F2, and we know that if I want to find the net force, the resultant force, other ways that's put it often, I basically just need to sum those two force vectors, F1 and F2. Now... plus F2. We need to add the force vectors. Now, you can either do this geometrically, if you wanted to. You could do it geometrically by drawing a diagram to scale, basically, of each of these forces. Then you could move one tip to tail. Like, we could move F1 to the left, and then we could connect them. That'd be one way of doing it. Probably an easier way of doing it is what? What's the way we learned Physics 1A to do this? How would I add this vector and this vector? What's the easiest way to do that?
Add the components.
Add the components. That's exactly right. So what we're going to want to do is find the value of F1 and the value of F2. We will then break them up into components. F2 is already pointing along the x direction. We don't need to break it up. We just need to break up F1. Okay, let's go step by step through this. Let's start over here. Let's see. So F1 is going to be equal to... Remember that the general equation that we're using for this is the electric force equation, and that is equal to K, Q times Q divided by R squared. And we'll say it's 1 and 2, for example. Although not at any point in this problem are we going to be using 1, 2, so really we're going to be doing things like between 1 and 3, for example. Okay, the force F1 is going to be exactly that. It's going to be the constant K times Q1 multiplied by Q3. We want to find the force between 1 and 3 here, the force that we're calling F1. And we're going to divide by the distance between them squared. I'll just go ahead and write down in here that the distance between them is the square root of 2 times A, and we're squaring that. Let's immediately plug in these values. K is 9 times 10 to the 9. As much as you hate doing it, I'm sure, be sure that you write these units down all the time until you get really, really, really confident with this stuff. And even then, you should still continue to do so. 5 microcoulombs will be 5 times 10 to the negative 6 coulombs. And they are both the same. I'll write it again. I could square it, but just to make it really clear. In this case, Q1 and Q3 both have the same value. And then we're dividing by root 2a. Root 2 squared is just a 2, and then we'll have a squared, which was 0.1. Hopefully, by skipping that step, it's not too confusing. We then calculate the value of what this is. Can we do this on our heads? Why don't you calculate this for me, and I'll see if I get it right. It looks like it's kind of hard. Let's see. 10 to the negative 12. 10 to the 9. You get 10 to the negative 3. This is 10 to the negative 2. So negative 3 plus 2 would be negative 1. And then we have to do the other stuff. 25 multiplied by 9. See, you get divided by 2. That makes it really hard, right? So it's 4.5 times 25. So it's like 112. That can't be right. Is that right?
1125.
I got 2.25 newtons, but I'm not sure if that's right.
So this would end up being, 11.25. Okay, well, there we go. That's F1. Here, we'll write this right here. That's F1 right there. We'll be using that again. Ooh, that looks really bad. Anyone else get 11.25?
Yeah, I got it.
Excellent. Okay.
Yeah.
So that's F1. Okay, let's do F2 over here. So F2 is going to be equal to, now this is the force between 2 and 3. We're not going to, this is something that's important, that is a question that I know a lot of people will ask. Do not worry that this is a negative sign, okay? We already know that F2 goes left, right? All we care about is the magnitude of this, okay? So when you plug in the numbers, we're just going to plug in the magnitude of the values here. So we'll be doing K, Q2, Q3, divide by the distance between the square, which is A in this case. I don't care that Q2 is negative. I don't care that this is positive. We're just going to find the value of this, and we'll worry about all the other stuff later. So F2 is equal to, we'll have 9 times 10 to the 9. And then we're multiplying by Q3 was 5 microcoulombs, the other one's 2. So let's see, we'll do it in order. So Q2, 2 microcoulombs, so 2 times 10 to the negative 6. Hopefully we can fit this all in here, and we'll have 5 times 10 to the negative 6 as well. Pretty much fits in there. And we're dividing by a squared, which is going to be 0.1 meters squared. So F2, this is a little easier to do because the 2's, there's no 2 down here anymore. So again, it's 10 to the 9, 10 to the negative 12. That becomes negative 3. This is 1 times 10 to the negative 2 when you square it. So negative 3 plus 2 is negative 1. And then we do everything else, which is 10 times 9. That's easy. That's 90. Yeah, so 9 newtons. So 90 times 10 to the negative 1 newtons is equal to 9 newtons. So that's F2. I'm not doing this math stuff to show off. I'm doing it to teach you something, which is that you can often figure out what your answer should be without using your calculator. And in this class, that is really, really helpful. Now, quite often, these coefficients here may be kind of nasty. It may be like, well, this is always going to be 9, right? But this may be something like 4.5, and this may be something like 7.2. And then it's going to be really hard to check your answer, right? But what you can always do, yes, F2 is the force of 2 on 3. That's right. That's right. In fact, I don't know why I left that out. I should really just do this. This is F13, this is F13, and this is F23, and this is F23, okay? Yeah, because I remember learning somewhere that I'm not supposed to make those shortcuts. I was just trying to make it a little bit neater, but good question, Andrew. Okay, so again, all I'm talking about here is order of magnitude estimations of your answer, right? So to do that, all you have to do is to look at the exponents. Don't worry about anything else. Just say 10 to the 9, 10 to the negative 6, 10 to the negative 6. What is that? 9 minus 6 is 3. 3 minus 6 is negative 3. And then just go from there, and you can get an idea of what your answer should be. You can always check your work before you get the answer, which is really helpful in a class like this, because you're multiplying numbers that are gigantic or really tiny. So now we want to combine these together. We need to vector sum both of these forces, right? F13 and F23. And again, to do that, we said we're just going to use components. So how do we use components? Well, it's been a while since you did this. That the way we do components is basically you take your vectors and you split them up into vectors that are parallel to your axes. Oops. Like this. You take vectors that are parallel to your axes and say, well, these components will then add up to that main vector. And in order to know what the components themselves are, you just need to know what the value of this angle right here is. In this case, the value of that angle is going to be 45 degrees. And we know that because this is A and this is A, which means this is a 45, 45, 90 triangle right here. So we know the value of theta, which means that we can find the value of these two components right here. And they're going to have values that we could call, for example, f1x if we wanted to, and we could call this one f1y, where f1x is going to be equal to f1 times the cosine of 45 degrees, and f1y is going to be equal to f1 times the sine of 45 degrees. So what are those equal to? Well, f1x is going to be equal to 11.25 times cos 45. That's equal to, are we in degrees? Yeah. 7.95. And they're both going to have the same value. Okay, and then just for the sake of reintroducing unit vectors to you in case you've forgotten, this type of a vector can be written in the following sense. The force of 1 on 3 can be written as 7.95 newtons times I hat plus 7.95 newtons times j hat, right? And our force F23 can be written as a, in similar ways. It's 9 newtons to the left, which can be written as negative 9 newtons multiplied by I hat. And then if I want to sum the two forces together, I can just, since they're already written in these forms right here, I just basically add together F13 plus F23. So that's going to be equal to, let's see, 7.95 I hat minus 9 j hat will show up here. So 7.95, sorry, they're both I hat. I didn't say that right. 7.95 minus 9 I hat plus 7.95 j hat. And of course we know that all of this is in the units of newtons. Okay, what is that going to be? That's almost 8, so this is pretty close to, is it 1.05? Is that what that is? I hat plus
Yes.
7.95 j hat, and then that's all in newtons. And that is the net force in unit vector notation. Of course, we can write this in polar form by squaring the components, right? Like we can find the magnitude of the force. In case you don't remember, the magnitude of this is given by taking 1.05 squared plus 7.95 squared and square rooting it. And then of course we can put in, oh, this is negative. Thank you for check. That is negative right there. I'm so sorry about that. That's the negative 1.05. Thank you. Okay, but this is of course a perfectly acceptable answer. If the problem asks you for magnitude, you'd have to do this. And if it asks you for direction, you can obviously find the direction of that. What does that vector look like? It's a negative 1.05 plus 7.95. So if we were to actually draw that on our picture right here, shapes, please, shapes. Ah, yes, it doesn't want to give me a shape right now. It's stuck on something. Shapes. Is it because, okay, I'm not touching the thing. Just what a shape. Ah, yes, there it goes. Shape. Okay, negative 1.05 I hat, 7.95 j hat is going to be pointing up 7.95 and then left a little bit. So that's our net force. Somewhere off in that direction. Is that exactly right? No, probably not, but that's the net force. Is that reasonable? Well, I guess. I mean, it looks like the negative charge won because it's not being pushed to the right, right? It's being a little bit more pushed to the left, but it's being generally pushed up because the positive charge gives it an upward force while, oh, you know what I should do actually if I want to make this really accurate? I mean, it's not very accurate as it is. Come on. I often wonder if I had a better computer if this stuff wouldn't happen. Because all I want to do, I just want to select this. That's it.
OneNote's pretty bad sometimes, so.
Yeah. Ah, there it goes. It's selected. Sorry, I should have made it so that the y component was exactly the same, right? That's what I should have done. Because we know that the y component of this vector is the same as the y component of that vector right there. So that's a little more accurate drawing like that. Should I use something different from OneNote, do you all think? It works well enough. It's just these really strange things where
It's when you have a lot of pictures on there.
Yeah.
I think that's where it like suffers.
Do you think it matters that I have all these other courses that are still back here? Like,
Probably not.
yeah, I have a pretty strong computer. I mean, it can run games really well, but it's not top of the line. It's like an i5. It's probably 6 years old. I don't know. Anyway. Okay, let's keep going, though. I don't want to get too distracted. I definitely want to talk about electric fields before we leave today. So, did anyone have any questions about this problem? Y'all think you can do that okay? Just vector addition, right? Don't forget that force is a vector. So anytime you want to find net force, you have to do vector addition, right? Superposition of forces. All right. Today, the last topic for today, and this is something we will not complete today, but we will keep talking about over the next 2 weeks, really. So, yeah, let's talk about it. Electric fields. This is a pretty. It's a really simple idea that I promise you in a few weeks it's going to seem really complicated too. So it's going to start off seeming really simple, and then as soon as we start applying it, you're going to forget what it really is. So I want you to focus very strictly on what I'm about to say, because this is what you need to remember when it comes to electric field. So let's say that I have a charge, okay, and I'm going to place this charge right here. Okay, it's going to be kind of a point-like charged particle, but I'm going to label it with a capital Q, like this. And I'm going to give this a name. I'm going to call this my source charge. Okay. And then what we'll do is, near this charge, we're going to come to some point in space right here, P. And at that location, we're going to imagine, and when I say imagine, we're imagining. That means this isn't a real thing. We're going to imagine that at this location right here, we place what's called the test charge. Okay, so at the location P is just a point in space. We're going to place what we call a test charge. It's going to be a very small charge, and we're going to label it as Q sub 0. Okay, and we're going to place it right at the point P. Okay, we call that our test charge. And the charge is basically going to do exactly what it says. It's going to test the size of what we call the field that's produced by this object. Now, in order to do that, what we do is we say, supposing that both of these were positive, just to keep things simple, what would the direction of the force on Q0 be? So we assume that our source charge is kind of fixed in place. So we'll say that this is fixed in place. It's not moving. What would the direction of the force on the test charge be?
To the right?
Be to the right, right? Yeah. So we have a force in this direction, and that would be, what we obviously call the electric force. And of course, it's dependent on the distance between these two objects. We should probably include that in our little picture here. So what we could do, in fact, we might as well draw a vector, because we can, and it's useful in this case. So let's go ahead and draw a vector, and we'll use, what have we not used yet? Blue. And I'm going to label that vector as R. So we'll come over here and define what that is. So R is going to be what we call the position vector. And it really just tells us the position that we're looking at, point P, right? Now, what is the size of our electric force in this case? Well, we know the size of that electric force is basically equal to a constant that we call K, multiplied by big Q, which is the source charge, multiplied then by our test charge, which we're calling Q naught, and we're dividing that then by the distance between the two of them, which is called r squared. And if we want to include the vector r in this, what we could do is say that the direction in this case is given using a symbol that we call r hat. Now, what is r hat? So if I have a vector like r, go ahead and draw our position vector over here. So I've got a vector like r right here, right? You're supposed to switch colors when I click this. There you go. And if I want to define what a unit vector is, the unit vector is basically a little tiny vector that points exactly in the same direction as the vector r, but has length 1, okay? We call that r hat. So if r is the position vector, r hat is the unit vector that points in that direction, okay? And it has a value that we can always find by taking the vector r and dividing by its magnitude, right? If I take a vector and I divide by the magnitude, the length of the new vector is guaranteed to be 1, so r hat is that vector. Okay, so we could actually use this as a way to define what the direction of the force is, right? It points in the r hat direction. It points along r, this way, right? And then if we changed our source charge to a negative charge, it would obviously flip around the direction of the force. So this would kind of work out pretty well. Now, what we'd really like to do now is to get rid of the test charge. We'd like to understand what effect electricity has at this location in space P, even if there was no test charge there to feel it. Why do we want to do that? We like to come up with an understanding of how electricity affects this point in space, even if there was nothing there to feel it, right? That's our goal. And the way that we do that is we say, look at the ratio of the force divided by the charge, the source charge. If I take the ratio of the force divided by the source charge, in this case, what that ends up being equal to is K times capital Q divided by r squared multiplied by r hat. Okay? And when we do that process, when we take the force and we divide by the source charge, what we're left with is something that we call the electric field E. The electric field E. And then what we can do is we can look at this piece of the equation and this piece of the equation, and we can write a really simple equation here. The size of the electric field at point P is equal to the force that's placed on a source charge divided by the size of the force of the source charge. That's electric field. So we're using the symbol E for electric field. So when I write a capital E with a vector above it, I mean electric field always. Okay? A little e is the electron charge. A big E is the electric field, right? It is basically the force per unit charge. It can be written another way. We can actually now define what force is in terms of the field. The electric force is no longer given by Coulomb's law. It's instead given by taking the source charge multiplied by the size of that electric field at that location. That's our force definition, and that's our electric field definition. Okay? The electric field exists at a point in space, whether or not there is a charge there to feel it or not, but as soon as you place a charge there, the size of the force is equal to the value of that test charge multiplied by the electric field at that location, okay? That is what an electric field is. Does anyone have any questions? It's a really simple idea, but it's really powerful too. And I'm going to go into more details, but please, if there's anything that I said that you didn't understand, please ask now. And I'll give you a couple minutes because people are often take time to take things in. Does it make sense what I mean when I say the word electric field?
Can you explain the definition again?
Sure. Okay. So the electric field is...
For the electric field.
Mm-hmm. Yeah. So the electric field is what would happen if you place a charge at a location is we would say there's a field there that we call the electric field. It's the effect of electricity. And if I place a charge there, it's going to feel a force. Now, one way to talk about that is Coulomb's law. We already learned that, right? We're learning a second way to talk about it. The second way is to say that even if the test charge wasn't there, there would still be a field that we call the electric field. And when you put the charge there, the size of the force that the charge feels is equal to the size of the field multiplied by the charge. Okay? Did that help to explain it all?
Sort of.
Let me give you an example. So let me tell you, let's say...
The textbook uses like gravity as an example.
Yeah, I was
Like
about
force
to.
of gravity.
I'm about to use gravity as an example, but I wanted before I did that, I want to make it clear what we're talking about. So I was going to give you an example of a couple different electric fields. So let's talk about what electric fields actually kind of look like real quick. Now this is kind of complicated. We're gonna start complicated. We're gonna go simpler. So if I place a positive charge here, positive Q, right? The way that the electric field works is that if I were to come to any position near this object here, I would say that I can draw a vector, okay, and that vector is going to represent the size of my electric field. So this vector is going to be what we call the electric field E. And the tendency of this electric field is it's always going to kind of point away from the charge, right? And if I go in a circle so that I'm always the same distance away, then the size of these vectors will all be the same. Okay, so if each of these points, right here, 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 all these 8 points, if they're all the same distance away, then the size of the electric field at those locations is all the same. Okay? All right. This is what we call a vector field. At every point in space around this charge, you can draw a vector to represent the size of the field. Now, as I go farther away, the size of the field is going to get weaker, so we represent that by a slightly smaller arrow. As I go farther away, the field gets weaker. Just like when you go farther away from a source of sound, the sound becomes less intense, so does the size of this electric field. These vectors out here are slightly smaller than the vectors in here. And if I were to come in here closer, I would get an even bigger vector, okay? I don't know if I have enough room here to really show that, but yeah, these vectors that are close would be bigger. And this would produce what we call a vector field. A vector field that basically looks like a spider web, pretty much, okay? Where these are small, maybe this is medium, and maybe this is large. The closer that you get to the charge, the bigger the field that you feel. Does that make sense? But yeah, a field, in this case, a vector field, means that at every point in space around this object, I could come over here and say, there's an electric field here. It's a really small electric field, but there's an electric field there. Since the electric field's a vector, you need two numbers to describe every point in this space. Okay? Now that is a slightly complicated vector field to understand, but what I can say is that if I place a point charge at this location, right here, our test charge, right? What direction is the force that it's going to feel? I put a positive charge here. What's the direction of the force that it feels?
Repulsive.
Yeah, it's going to point that way, right? And the size of the force that it feels is just equal to the charge times the field. And that's it. The force and the field are in the same direction. If our charge was negative, the force would be the opposite direction. So you can actually put a negative charge in here and it'll fix it the right direction. Now, to understand this type of a field, it's really probably too much. So we're instead going to look at a much simpler field. A much simpler field to consider is this type of a field. If I take a plate, and by plate I mean a metal plate, okay? And I'm looking at an edge on, and I charge one metal plate with a positive charge. How do I do that? Well, we can use battery. Okay, so let's say that I've got a battery, and this is the positive side and this is the negative side. And then I take a little red wire and I connect it from the positive side to this plate, and I clamp it onto the plate right here. Okay, and then I have separated from it by some distance, I have another plate, and with this plate, I basically take a battery. And we haven't talked about what batteries are, but I think you guys kind of have probably seen batteries in today's modern world. And I take a black wire, doesn't really matter that it's black, but just black for negative and red for positive. Then I'll get a positive plate and I'll get a negative plate, okay? And if I put these plates close enough together, it turns out they produce a really simple electric field that we're going to study a lot in this class, which is called a uniform electric field, okay? And the direction of that electric field is going to be something like this. And I'm going to try as much as I can to space these lines out equally to represent that there's no region where the field is stronger or weaker. It's constant, okay? Now, that's our electric field right there, okay? Now, let's give it a value. Let's give it a really simple value, something that we can do calculations with. Let's say the electric field between our two plates is equal to 10 newtons per coulomb, okay? Newtons per coulomb because, again, it's... Oh my god, stop doing that. It's force per unit charge, right? So let's say that we have what we call this would be called a uniform electric field. At every point in this space, we have the same value, okay? All right. So now, if I was to place, again, let's do a positive particle to keep things. So I take a positively charged particle right here, and I tell you that the size of that particle, Q naught, is, let's say it's equal to 5 microcoulombs, okay? Now, positively charged particle. It's going to be repelled from the positive plate, but it's going to be attracted to the negative plate, right? So the direction of the force on this particle, it points in the same direction as the electric field, right? That's the direction of the force. And the value of the force, well, that's given by that equation right there. The value of the force is going to be equal to the size of our charge multiplied by the size of the electric field. And just to make things even better here, I should have done this to begin with. Let's actually say that the direction of our electric field is negative j hat, because it points downwards, okay? Negative j hat. And then we can actually include that in here. So then the size of the force, well, that's going to be equal to the size of our charge, which is 5 microcoulombs. And we multiply that by negative 10 newtons per coulomb j hat. And we get a size of a force that's equal to about 50 micronewtons. And it's also pointing in the negative j hat direction, right? So if you know the electric field and you know the charge, the force is just the charge times the field, right? Does that make sense?
Yes.
You all have to remember this. You have to promise me you're actually going to remember this. Because I'm going to ask this question over and over and over again, where I'll say, okay, now that we have the electric field, if we want to find the force, what do? You just multiply by the charge that you place there, okay? Now, the thing about the electric field is it exists whether or not there is a charge there to feel it or not, okay? That field was already there, even though you didn't have a charge to feel it, right? So the best comparison for this, for something that you've learned before, is exactly what, I think it was Barron that said this. We can compare this exactly to the gravitational field of our planet. So if this is Earth, then the Earth has what we call a gravitational field, and we use the symbol G, right? And what's the value of it? Well, it's about negative 10 meters per second squared multiplied by j hat, where j hat is just the downward direction, right? And what does that look like? Well, it looks exactly like the field between two plates. You get a gravitational field that points everywhere downwards, like this, right? And if I want to find the force on a massive object, so our massive object is going to be some mass m, how do I find the force on this mass? We know it goes down, right? But how do we actually find the value of it?
Just mass times the acceleration due to gravity.
Yeah, exactly. Or mass times the gravitational field. This isn't the acceleration due to gravity. It's the gravitational field of our planet. Yes, gravity accelerates at about 10 meters per second squared if you're just going to talk about acceleration, but this is gravitational fields. Just like electric fields. This is gravitational field. And to get force, you do exactly the same thing. You take the mass times the field, right? So can you see the similarities? The G is like the E. Electric field, gravitational field. Now, this is another thing that I want to kind of emphasize about this here. If you think about the gravitational field of the Earth, you probably don't think about it much unless an object is falling, right? We don't really care that the acceleration due to gravity is 10, except when an object's falling, because that's when it matters, right? Is when the object actually falls. But none of you would doubt that there is a gravitational field of Earth, right? Is there anyone that wants to doubt that the Earth has a gravitational field? Even if there was nothing there to ever feel it, it would still be there, right? The mass of the Earth kind of alters the space near the Earth such that it attracts things to it, right? And there's different ways you can talk about that. You can talk about that with forces if you want to, or you can talk about it with fields. It's two different ways to talk about the same thing. But they're not the same thing, right? A field and a force, they're not the same. They're different, okay? To go from a field to a force, you need something to multiply by, okay? They are both vectors, but they're different. It's a different way of describing exactly the same thing. You did this in Physics 1A, right? You learned Newton's laws, and then you learned about work and energy. And you learned you can solve problems using either Newton's laws or by using work and energy. There's two different methods of solving the same type of a problem, right? The electric field and the electric force, in certain problems, you're going to want to use the electric field. And in certain problems, you're going to want to use the electric force. And I'm just going to say now that the electric field itself is very fundamental to electricity, and understanding how it works and being able to demystify it for yourself is really important in this class. So I'm going to just roughly go back through what we said again. Electric field is defined by starting off with a source charge and saying if I come to some point P in space, right, that I can define an electric field at that location by using a test charge, finding the force that it would feel, and then dividing by the test charge to get rid of it. And that defines an electric field. It's the force per unit charge, just like this is the force per unit kilogram, right? Do you all understand that? Force per unit charge, force per unit kilogram, right? But the field is a very real thing. And alterations within this field can propagate through space. Electric fields exist all throughout space. They have infinite range, okay? As far as we know. At least as far as the size of the universe or whatever. And fluctuations, tiny little fluctuations in this field can be detected, right? Let's compare this to something that you may be a little more familiar with, which is sound. So the phenomenon of sound, right? When you hear a sound wave, you don't really hear a wave, right? But you kind of probably know that you can represent sound with waves. What your ear is sensing is tiny little fluctuations in the pressure around you, right? Does that sync up with what you guys understand? That your ears, what you're hearing are pressure fluctuations, right? So when your eyes see things, your eyes are literally observing fluctuations in this thing. The electric field. That's what sight is. Your eyes sense little tiny variations in the electric field in the space around you. Yeah? Yeah, Barron's right. It's a confusing concept. It's definitely worth reading this section. Because it's almost like a magic trick in a way, because you basically say, okay, we're going to define this thing called the field by introducing two objects and saying, we know how to define the force between two charges because of Coulomb's law, right? So we just define that force. Well, there it is. But then we say, but what if we got rid of this charge? It didn't matter in the first place. Let's get rid of it. And once we do, we're left with the field. So it almost feels like you're kind of going in a circle, and it almost feels like you didn't really do anything. But what you did is huge. And what we're going to find is that defining the electric field around objects and then using that information, it becomes very powerful. And I don't think you really feel the impact of this. I'm not even touching the keyboard that did that. That was weird. What we'll find out is, toward the end of this class, that we can describe the phenomenon that we call light as fluctuations of this field. So a question that Cam said is, do you regard it as something real or just a mathematical concept? Or is there much of a difference between reality and the mathematical concepts which describe reality? That's a really good question. Is this thing real? I mean, for all intents and purposes, it feels like just a mathematical construct. But I promise you that by the end of this course, you won't think that anymore. Like, it starts off as feeling like a mathematical construct, but later on you're going to realize that this thing, the fluctuations within this, are what we call light, right? So the fact that you're seeing different colors, like you see my shirt is whatever, red, and my glasses are black or whatever, this sensation of vision is a sensation of fluctuations within this field. So I mean, I would say it's not only a mathematical concept, it's something that very much describes our reality. Yeah, so kind of running short on time here. Could do one problem. 3 minutes. We don't have time to do this. So what I'm going to do is we will do this at the beginning of class next time. And I'll just throw it up here, and we'll just talk about it a little bit. Paste. Oh, I love how I pasted it back up there because I didn't move my... All right, we'll just slowly drag this down. Slowly drag this down. Come on. Yeah, I think you're right that the kind of more images you get on these documents, the worse it gets. Maybe I should split each section of the lecture up into a different tab or something. I mean, because this thing is just, it won't move. Let's try it again. Cut. All I want to do is just move this. That's it.